Welcome to G Fun Facts Online. For centuries, the thousands of planets we've discovered outside our solar system were just dots of light, whispers in our data. But that's changing. We are now standing at the dawn of a new era, an age where we can take those distant dots and transform them into three-dimensional worlds with weather, climates, and chemistries that we can map. This is the dawn of 3D exoplanet cartography, and it's providing powerful new tools in our quest to find life beyond Earth. Today, we're going to explore how we're peering into alien skies, what groundbreaking discoveries we're making, and what it means for one of humanity's most profound questions. Let's get started. The journey to mapping alien worlds has been a long one. The modern age of exoplanet hunting really kicked off in 1995 with the discovery of 51 Pegasi b, a type of planet we call a hot Jupiter. It was found using the radial velocity method, which is a clever way of seeing a star wobble as a massive planet gravitationally tugs on it. This was huge. It proved planets around other stars were common, but it only told us the planet's mass and orbit, nothing about what it was actually like. The real breakthrough came with the transit method. If a planet's orbit is aligned just right, it passes in front of its star from our point of view, causing a tiny, temporary dip in the starlight. This lets us figure out the planet's size. But more importantly, it gives us a chance to study its atmosphere. As the star's light filters through the edge of the planet's atmosphere, gases absorb specific wavelengths, leaving a chemical fingerprint in the light that reaches us. This is called transit spectroscopy. Our first major success with this was in 2001. Using the Hubble Space Telescope, astronomers detected sodium in the atmosphere of a hot Jupiter named HD 209,458b. After that, we started finding water, methane, and carbon dioxide on other worlds. But these were still limited, one-dimensional snapshots. They gave us an average composition across the whole atmospheric limb, but they couldn't tell us about weather or climate. To truly understand these worlds, we needed better tools. At the heart of it all is spectroscopy, the science of splitting light into its rainbow of colors to see what something is made of. We've already mentioned transit spectroscopy, which analyzes starlight filtering through an atmosphere. But there's a complementary technique called secondary eclipse spectroscopy. This is when we watch the planet pass behind its star. Right before it disappears, our telescopes capture the combined light of the star and the planet's hot, glowing day side. While the planet is hidden, we just see the star's light. By subtracting the star's light from the combined light, we can isolate the light coming directly from the planet itself. This gives us crucial information about the temperature and composition of the planet's day side. Then there's direct imaging. This is exactly what it sounds like, taking an actual picture of an exoplanet. It's incredibly difficult because planets are billions of times fainter than their stars. It's like trying to spot a firefly next to a searchlight from miles away. To do it, astronomers use instruments called coronagraphs that block the star's blinding glare, allowing the faint light of the planet to peek through. This technique works best for big, young planets that are still glowing with the heat of their formation and are far from their star. But perhaps the most powerful technique for understanding dynamics is high-resolution spectroscopy. This method allows for incredibly detailed measurements. It can resolve individual spectral lines, and by using the Doppler effect, it can measure their motion. As parts of the planet's atmosphere spin towards us, their light shifts slightly to the blue. As they spin away, it shifts to the red. By tracking these tiny shifts, astronomers can measure the speed of winds, detecting powerful jet streams and complex weather patterns. This was one of the first true glimpses into the 3D nature of alien atmospheres. And all of these techniques have culminated in the key method for true 3D mapping, spectroscopic eclipse mapping. This is where the magic really happens. As a planet passes behind its star in a secondary eclipse, different parts of its day side are gradually hidden. By taking incredibly precise measurements of the dimming light at many different wavelengths, astronomers can reconstruct a brightness map of the planet's face. And here's the brilliant part. Different wavelengths of light probe different depths in the atmosphere. So by creating brightness maps at multiple wavelengths, we can stack them together to build a full, three-dimensional temperature map, revealing the thermal structure of the atmosphere in latitude, longitude, and altitude. The James Webb Space Telescope, with its huge mirror and incredible sensitivity to infrared light, is the perfect machine for this job. It has the precision to catch the tiny variations in light needed to create these detailed maps, officially ushering in the era of 3D exoplanet cartography. Of course, this work is filled with immense challenges. The signals are unbelievably faint, and astronomers have to fight against stellar contamination, things like star spots that can mimic a signal from the planet. For ground-based telescopes, our own atmosphere's water and oxygen can block the very signals we're looking for. But with advanced models and the sheer power of new observatories, we're overcoming these hurdles. The results are already spectacular. Take WASP-18b, an ultra-hot Jupiter, about 10 times the mass of our Jupiter, which orbits its star in a mind-boggling 23 hours. Its dayside temperatures approach 5,000 degrees Fahrenheit. Using JWST and spectroscopic eclipse mapping, astronomers created the first ever 3D temperature map of this world. It revealed a scorching hot spot where the starlight hits most directly, but the map also showed that the planet's winds aren't very good at spreading that heat around. Most remarkably, the map showed that this hot spot has less water vapor than the surrounding atmosphere. This is the first direct evidence of a long-held theory. At these extreme temperatures, water molecules are literally torn apart into hydrogen and oxygen atoms. Seeing this process, called thermal dissociation, happening on another world is a monumental breakthrough. Another fascinating case is WASP-121b, a puffy, marshmallow-like gas giant about 900 light-years away. It's tidally locked, with one side permanently facing its star. Using instruments on the Very Large Telescope in Chile, astronomers mapped its atmosphere in 3D by tracking different elements. They found a powerful jet stream whipping around the equator, creating violent turbulence. In the lower layers, they detected winds carrying iron and titanium across the sky. This suggests that on the cooler night side of the planet, these elements could condense and fall as metal rain. The sheer complexity of the weather on WASP-121b, with its distinct layers of wind and chemistry, is unlike anything in our solar system and shows just how diverse planetary climates can be. This ability to map alien climates has profound implications for the search for life. A planet's climate is a key factor in its habitability. To find life, we look for biosignatures, things like specific gases that are unlikely to be produced by geology alone. One of the holy grails is finding both oxygen and methane in the same atmosphere. These two gases destroy each other, so if they're both present in large amounts, it suggests something is constantly replenishing them. On Earth, that something is life. But the universe is tricky. There are non-biological processes that can create false positives. For example, intense ultraviolet radiation from a star can break down water vapor to produce a lot of oxygen, with no life involved. This is where 3D climate models become essential. By giving us a detailed picture of an exoplanet's temperature, pressure, and circulation, we can determine if the conditions are right for one of these false positives, or if a biological source is a better explanation. These maps can also help us pinpoint potentially habitable zones on otherwise extreme worlds. A tidally locked planet might have a scorching day side and a frozen night side, but in the twilight region between them, the Terminator Zone, temperatures could be just right for liquid water. 3D models can help us find these promising niches. And this is just the beginning. The JWST will continue to map more worlds, from gas giants to smaller, rocky planets. But the next generation of observatories is already on the horizon. The European Space Agency's Ariel mission, launching in 2029, will be dedicated to studying the atmospheres of around 1,000 exoplanets, giving us a huge statistical sample of alien climates. Looking further ahead, NASA is planning the Habitable Worlds Observatory, a massive space telescope designed to directly image Earth-like planets around Sun-like stars and search their atmospheres for signs of life. As our technology advances, some scientists are even looking at